Hi, everyone. Congratulations are due to most of you for surviving all three of the CS61B projects. Hopefully, most of the hard work is over now. Take a deep breath. Relax. Then enter the network tournament when you're done relaxing. I want to warn you all that today's lecture is probably going to go 5 or 10 minutes over time, and if you have to leave early, that's fine. I won't be offended, but I think that this topic fits in 60 minutes and not 50, so I'm probably going to go until about 5:10. And today's topic is randomized analysis, and in a way it's a little bit like amortized analysis because it's about proving the average running time of an algorithm, but it's different too, and the way it's different is like this. When you use amortized analysis on a splay tree, you're proving that even though one splay tree operation could be very slow, if you do a bunch of splay tree operations, starting from an empty tree, that on average, they'll be fast. And when you look at the whole sequence of splay tree operations, starting from an empty tree, you still have an absolute guaranteed good upper bound on how long all those operations will take together, even though one of those operations might be slow. Randomized analysis is a little bit different. It's also about proving the average running time of an algorithm, but for a very different, well, very mathematically different anyway, notion of average. So in a randomized algorithm, well, quicksort usually runs in n log n time on average. But in the worst case, it might take n squared time. So we don't have the good n log n guarantee on the total running time of your program, but if you run quicksort over and over and over again an infinite number of times, then I can guarantee that the average running time will be n log n. And so that's a very different idea. Remember that randomized algorithms make decisions based on basically a roll of the dice. And so you call your random number generator and you get a random number, and based on that you decide what to do. Now, the random numbers actually help keep the running time of quicksort and quickselect low. On the other hand, a randomized algorithm will occasionally run a little bit slower than expected just because you got bad rolls of the dice. So the randomized algorithms that we've seen are quicksort and quickselect. But there's one other as well. It's not an algorithm that we actually advertised as generating random numbers, but hash tables can be analyzed probabilistically as well. And the reason is because in an ideal hash table, we would have a random hash code. And the random hash code is what helps reduce the number of collisions and keep that under control. So before I can start analyzing these algorithms, I want to give you a little bit of very basic probability theory, just enough to get through this lecture. And those of you who've taken a probability course, this will all be old hat to you. But for those who haven't, there's one main concept that we need to use in this to understand how to analyze randomized algorithms, and that's called expectation. And so here's the idea. Suppose that we have a method called x, and you can call x, and when you call x, what does it do? Well, it flips a coin. And the running time of x, well, x goes and does some other calculations, and the running time of x is going to depend on whether we got heads or tails. So if it comes up heads, then x will always take, let's say, 1 second to execute. But if it comes up tails, then it takes 3 seconds. Now, the way that we formalize this is that we have something called a random variable. We're going to call it capital X. X is the running time of one call to X. Well, what is X? I mean, big X is sometimes 1 and sometimes 3, so it's not really a number. It's like sometimes one number and sometimes a different number. And that's what I mean when I say it's a random variable. Now, the idea is that with probability 0.5, in other words, half the time, big X is 1. Half the time it takes 1 second for our routine to run. And on the other hand, if we have tails, which also happens with probability 0.5, the other half of the time, then X is 3. And so again, that's why X is called a random variable. Now, we say that the expected value of X is the average value that we're going to get for X if we do the coin flip an infinite number of times. Now, expected is a formal mathematical term that means average, but it means average in the sense of probabilities. If you do something an infinite number of times, how is it going to turn out on average? Well, half the time it's going to take 1 second, half the time it's going to take 3 seconds, and so the expected time is going to be between that, 2 seconds. And here's how you actually compute it. First of all, here's the official notation for the expected value of X, E bracket X, close bracket. And that is equal to, well, what you do is you sum over all of the different possibilities the probability of it happening times the value you get if it happens. So with probability 0.5, it'll be 1. With probability 0.5, it'll be 3. So on average, our method takes 2 seconds expected time. All right. Any questions about this? Let's look at a code sequence where we do 2 method calls. Suppose we run the following code sequence. First, we do a call to X, and then we do another call to X. Okay, so the first call to X takes time X, where X is a random variable. The second call to X, well, if we flip the coin again, it might take a different amount of time than it did the first time. Like it might take 3 seconds the first time and 1 second the second time. So we need to give this a different random variable. So I'm going to give that running time the name Y, because X and Y are not always the same. Sometimes you get heads the first time you flip a coin and tails the second time. And again, Y is a random variable. Now, the total running time is the sum of those two. I'm going to call the total running time T. And since it's the sum of two random variables, it also has to be a random variable. Now, the question is, what is the expected total time for this code sequence? So the principle of probability that gives us the answer to this is simple and seems kind of obvious at first. It's called linearity of expectation. Linearity of expectation is a polysyllabic way of saying something very simple, which is that if you want to know the expected value of a sum of random variables, the expected value of that is always equal to the sum of the expected values of each of the random variables. So you can break this out like this. Now, you might be tempted to say, well, duh, but actually, things like this don't happen in probability very often. Like, this is true for addition, but it's not generally true for multiplication, or most operators. Addition is kind of special in probability. So, another thing that makes this magical is that it's true whether or not x and y depend on each other. Let me write down these values. So our expected value of our code sequence is, well, x will take 2 seconds on average, and y will take 2 seconds on average. So that comes up to a sum of 4 seconds expected time. Well, as long as x happens with probability 0.5 and y happens with probability 0.5, this is true even if x and y depend on each other. Like, for instance, suppose that we set this up so that y is always the same as x. If x comes up heads, then y comes up heads as well. If x comes up tails, y comes up tails as well. Then the probability of each coming up heads or tails is still 0.5, but now they're depending on each other. But the expected running time is still 4 seconds. And if they're opposite, if y is always tails when x is heads and y is always heads when x is tails, then the expected running time is still 4 seconds. But you can't do this with, say, multiplication and still have the right answer. Addition really is special in probability. Any questions about that? So the reason why linearity of expectation is important to us is because it means if the running time of your program is the sum of how long it takes to run a bunch of different methods, and each of those methods takes random amounts of time, you can figure out the total running time of your program by analyzing each little piece separately, figuring out how long it's expected to run, and then just add those all together. And let's see how that works in hash tables. Okay, the implementations of hash tables that we've studied do not use random numbers. So what are hash tables doing here? Well, again, we can model the effects of collisions by pretending that we are using a random hash function, or a random hash code to be precise. What do I mean by a random hash code? A random hash code is one that maps each possible key to a randomly chosen bucket. And for any one key, each of the buckets could be chosen with equal probability. So all the buckets are equally good, and we just choose one at random. Now, when I say a randomly chosen bucket, I do not mean that every time we hash a key, we roll the dice. No, you only roll the dice once per key, because for a hash table to work, the same key has to hash to the same bucket every time. So yes, every key has a randomly chosen bucket, but once that bucket's chosen, it stays that way forever. The reason we haven't used actual random hash codes in this class is because it's actually really hard to implement that. It's not completely impossible, but it's really hard to figure out how to do it. There is a number theoretical trick called universal hashing, which actually will allow you to generate a random hash code, though it doesn't allow you to choose out of all possible random hash codes, but it allows you to choose from a subset of random hash codes where they can prove that it's just as good as if you could choose from every possible random hash code. If you are interested in learning about that, it's in the CS 170 textbook that some classes use by Horman, Leiserson, Revestenstein. But even though people generally don't use that in practice because universal hashing is too expensive to use in practice, and people use sort of more quick and dirty hash codes, this is still a good model for how a good hash code performs. And having a good model is good enough to do an analysis. So this is a good model for how a good non-random hash code will perform. And the way that we judge hash codes in practice is by how closely they emulate this model, by how closely they behave just like a random hash code would. Now, to do an analysis based on random hash codes, we're going to make a few assumptions. Well, the usual assumptions. So let's assume that our hash table uses chaining. Now, chaining is the only way of handling collisions that I've taught in this class. Some of you might have heard about other ways, but we're going to stick with chaining because that's the easiest to analyze. And we're going to assume that there are no duplicate keys allowed in the table. So if you try to insert a key that's already there, the new entry will replace the old entry. That way there's never more than one entry in the table that has a certain key at a time. All right. So what I want to do is I want to analyze how long it takes if we perform one find operation on a selected key K. How long does that take? Well, so K hashes to a bucket, which, just for the sake of giving it a name, I'm going to call it B. All right, so the cost of, well, here's what we've got to do for a find operation. We've got to hash, find the bucket B. That can be done in constant time. Then we've got to search through the chain in bucket B until we find the item having the key that we're looking for, or we run out of keys and find that it's not there. So we're going to get charged proportionally to the length of that chain. Or in other words, we're going to get proportionally to the number of keys that hash to the same bucket. So the cost of the search is $1, which is the cost of hashing, finding the right bucket, and checking if there's anything in it, plus an additional $1 for every entry in the bucket V other than K. And that last cost is the price of collisions. Now I want to figure out what is the expected number of entries that might be in that bucket besides K. Well, suppose there are n keys in the table. Besides K. And I want to give each of these keys its own random variable. All right, so I'm going to set up a bunch of random variables called V1 and V2 and so on. Up to Vn. And for each of the keys stored in the hash table, it has its own random variable. And that random variable is it's chosen such that for any key, call it K subscript I, it's the random variable that goes with that key is set to 1 if that key falls into bucket B. And 0 if it hashes into any of the other buckets. So now, let's look at the cost of a find operation based on these random variables. The cost of find K is going to be equal to, well, there's a basic cost of $1, as I said before, for hashing. And then if key 1 hashes to the same bucket B as the key we're looking for, then we're going to pay $1 for that. But if key 1 hashes to a different bucket, then V1 will be 0, and we won't pay for that. And the same goes for key 2, and the same goes for key 3, and so on. Any questions about this? Do you believe me on this? So the expected cost of find K is the sum, well, we write it as E bracket T close bracket. And the way we figure that out, what the expected value is just linearity of expectation, which says this is 1 plus the expected value of V1 plus the expected value of V2. And so now we just need to figure out what each of these EVNs or EVIs is equal to. And here's how we figure that out. Well, remember that the table has capital N buckets. So each of these keys, like K1, it's going to get hashed to a randomly chosen bucket out of those big N buckets. So the probability of any key getting hashed to bucket B is 1 over big N. So for any one of those random variables, its expected value is, well, with probability 1 over n, it is 1, and otherwise it is 0. So the expected value is 1 over big N. And that's true for every one of those random variables. So we just add them all up, and we get the expected time is 1 plus little n over big N. And little n over big N, you'll recognize as the load factor. So when I've been talking about the load factor for the last month, I didn't just pull it out of my butt. It actually comes out of a probabilistic analysis. All right, so suppose that the load factor is bounded by some constant, like some reasonable constant, like 1 or 5. Then the expected value of t by that equation must be in big O of 1, which is what we're looking for. That's what we want out of a hash table. And this analysis applies for the insert and remove operations as well, because they also have to do the same thing, hash the bucket, look through the chain. And so all three hash table operations, insert, remove, and find, take big O of 1, expected time, if the hash table does not get resized. And what if the hash table does get resized? Well then, as you'll remember from Wednesday, hash table operations take big O of 1 expected amortized time. As long as you resize them to keep the load factor from going bigger than some constant. Any questions about that? So hash tables are the easier one to analyze. It takes a little bit more effort, or trickiness at least, to analyze quicksort. So here's the basic issue with quicksort. It's sort of like merge sort. You remember how we looked at why merge sort takes n log n time. You have a big array. You partition it into two pieces. Those get recursively partitioned into two pieces each. And you always have a nicely balanced recursion tree. And each level, the number of levels of the recursion tree is logarithmic. And the total work that you have to do at each level is big O of n. And that's where the n log n running time comes from. So that's what I said in the quicksort lecture. But if you look at, in the merge sort lecture, but if you look at quicksort, it's not as nice as this, because quicksort can give you pretty uneven splits sometimes. You don't get, in general, a 50-50 split. you get kind of 1/4, 3/4 splits on average because you're just picking a random pivot and using it to partition the array. And you don't know until you're done partitioning how big each half of the array is going to be. So with quicksort, your recursion tree might look like this. Start with the same block, and maybe this piece comes out small and this piece comes out big. And then this gets partitioned down a little more. And maybe the left piece comes out big and the right piece comes out small. And typically some parts of the recursion tree are going to go deeper than others. So, well, quicksort shares in common with merge sort the fact that each level takes linear time. Partitioning the lists Quicksort spends linear time on each level partitioning the lists. But when I say linear, I don't mean big O of n. I mean linear in the size of the level. So on this level, we'll spend $2 partitioning lists because there are 2 elements that make it down to that level. And maybe on this level, we spend $5 partitioning lists. And more on that level, so far on the way up. So it's not as easy to analyze quicksort. For one thing, it's hard to know what depth the tree will go to. That's hard to analyze. And so you can't really apply the same easy idea that we did to merge sort. But what you can do is you can look at one of the elements that you want to sort and ask yourself, for a typical element, how many levels down the tree does it survive? So maybe suppose there's an 8 here, and it winds up getting partitioned on the right side here, and partitioned on the left side here, and comes down here, and here's where it winds up. So I'm going to analyze for any one key, what depth do we expect it to go down to? So in a sense, the idea is instead of measuring vertical slices and then adding up, instead of measuring horizontal slices and adding up the horizontal slices, I'm going to take vertical slices, one for each key. I'm going to measure how deep the expected key goes down the recursion tree, and then I'm going to add that up over all of the keys. All right, so our goal is to analyze the expected depth that one input key, let's call it k, will reach down the recursion tree. And to make it simple, let's assume no keys are equal. And the reason for that is that that's the hardest case. If we have equal keys, then it's more likely to give us a balanced partition, not less. So unequal keys will give us the most unbalanced partitions. And now quicksort selects a random pivot, as always. And this random pivot is equally likely to be the smallest key or the second smallest key or the third smallest key or so on up to the largest key. So instead of thinking it in terms of which index are we picking the key at, those being equally likely, it's also true that the ith largest key being chosen is equally likely for every I. Now, for each of those keys, the probability is the same, 1 over n. There are n keys. Each one is chosen with probability 1 over n. And so since we want a reasonably well-balanced partition, let's say that the middle half of the keys are good keys. And the sort of half of the keys that are not near the middle are the bad keys. So to be a little more specific, let's say that the least n over 4, take the floor of that, keys, and the greatest n over 4, take the floor of that, keys, are bad pivots. And the remaining keys in the middle are good pivots. And again, I don't mean the keys in the middle of the array. I mean the keys with the middling values. Now, at most, half the pivots are bad. Another way of saying that is that the probability of choosing a bad pivot is at most 1/2. All right, so what happens if we choose a good pivot? So at least 50% of the time, we're going to get lucky and choose a good pivot. And if that happens, then we have a 1/4, 3/4 split or better. And that means that our chosen key, k, the key that we're tracking its progress down the recursion tree, will share a sublist with no more than 3/4 of the keys. And then that gets sorted recursively. But if you choose a bad pivot, then k might go into a partition with virtually all of the other keys. So essentially what I'm saying here is that there's a 50% chance that we might make very little or no progress. But we make progress at least half the time, and progress means that we get to throw at least a quarter of the keys away from the partition that K is in. Now, this is a pessimistic analysis, but it's good enough to get us the n log n bound for quicksort, so it'll do. We're going to have another random variable, and this is going to be a kind of weird random variable because it's actually a function of n. So it's actually a whole family of random variables, one for each value of n. So d of n is going to be a family of random variables, one for each value of n, which is less than or equal to the lowest depth that key k makes it to, when we sort n keys. The bigger n is, typically the deeper the depth that the recursion tree of quicksort is going to go to on average. So d is a monotonically increasing function of n, well, except that it's also a random variable too, so it varies from run to run. Okay. So based on everything I've said here, we can write down the following recurrence. The expected value of the depth that we have to go to for a particular key k when we are sorting n keys is, this is going to be an upper bound, so I'm going to use the most pessimistic assumptions possible. Now, if this is not the bottom of the recursion tree, if we haven't bottomed out yet, then we're going to have to go at least one level deeper when quicksort calls itself recursively. And then we flip a coin. And with 50% probability, we get a bad pivot. And if we get a bad pivot, it means we basically have to run the quicksort algorithm over again on virtually the same set of keys. So we'll just use a worst case assumption here so that we get the most pessimistic bounds possible and assume that actually we made no progress at all. So with 50% probability, we have to start all over again where we were before. But on the other hand, with 50% probability, we get a good pivot. And if we get a good pivot, then we throw away at least 1/4 of the keys. K is going to be with, at most, 3/4 of the keys we started with. And so that means the remaining depth that K is going to go to is 3/4 of n in the function d. Because we get to throw away 1/4 of the keys from that subdomain. Now, this is kind of an interesting formula because the thing that we're trying to solve for, E of dn, appears in it twice. So what I'm going to do is I'm going to eliminate this one by multiplying the equation by 2 and subtracting E of dn from both sides of the equation. So I multiply by 2, subtract E to the dn, and that gives me this. So that little trick simplifies this somewhat. What we've got left over is kind of interesting because it expresses d to the n in terms of some smaller d to the some smaller number. And this kind of inequality is called a recurrence. And there are a lot of algorithms whose running times are analyzed by solving recurrences like this. And when you take CS 170, you'll learn general methods for solving recurrences. Now, to solve a recurrence, you have to know what the base cases are, because you can't keep dividing by 3/4 forever. Eventually, you get down to the case where you've got maybe one element or even 0. And so for those special cases, basically we're going to assume that they don't cost anything. So the base cases of the recurrence are when we're down to 0 elements or 1, you can stop sorting. And now, for this recurrence, I'm not going to give you a technique for solving it. Instead, I'll just give you the answer. And you can check by substitution that the answer always works. So the solution is that the depth to which k goes, on average, can't be more than 2 times the log base 4/3 of n. The reason it's log base 4/3 is because we managed to cut the number of elements we're sorting by 3/4 at least 50% of the time. And so that's where those numbers come from. But the bottom line is that an arbitrary key k survives to a depth of Fego of log n. And so if a key appears in log n levels of the recursion tree, then it causes log n partitioning work. And so now that we know for any one key the expected depth that it'll survive to and the amount of partitioning work it'll cause, well, now we just add that up over all n keys. And we can do that by linearity of expectation. And by doing that, we find that quicksort runs in expected and log n time. Any questions on that? So I want to make some final points coming back to what the difference is between amortized time and expected time. Because I think it's important to understand this point. So quicksort is randomized because it uses random pivots. And quicksort with random pivots takes big O of n log n expected time, as I've just proven. But if you chose really, really bad pivots over and over and over again, you just at the casino and you're losing all your money as fast as you can, then the worst case running time is in theta of n squared. So that means that there is a small possibility that quicksort will run in quadratic time, but the probability of that approaches 0 as n grows. So as n goes to infinity, it's almost a sure thing it's going to take n log n time. You're more likely to be hit dead by a falling dinosaur from outer space than have your quicksort run in quadratic time on a million items. Whereas with splay trees, a splay tree operation takes log n amortized time. But the worst case for any one operation is linear. But splay trees are not randomized, and the concept of an expected time or a probability that it will take linear time is not a meaningful concept. If I take an empty splay tree and I insert the numbers 1 through n in order, and then I do a find operation, then it will take linear time, always. Because that's just a bad operation. I've set it up in a bad way. But it doesn't matter because the average time is still in log n, always. So a sequence of n splay tree operations starting from an empty tree never costs more than n log n time. Ever, ever, ever. There's just no concept that if you get unlucky, it might cost n squared time. That doesn't happen. And that's what amortized means. So let me review the 5 data structures we've learned that use these two concepts and what the amortized or expected times are. So we have splay trees, which take big O of log n amortized time per operation. We have disjoint sets, the tree-based version. Now, these always take order 1 time for a union operation, but they take big O of this fancy inverse Ackermann function, amortized time per find operation. We have quicksort, which this one's in expected, not amortized time. We have quick select, I did not cover that in class today, but if you're interested, I did put a couple paragraphs on it on the lecture notes. Once you've done quick sort, it's easy to do quick select too, and show that it's in big O of n expected, well, actually theta of n, just to be complete. And finally, we have hash tables. The CS61B poster child, because we revisit them again and again. And that's because they take theta 1. We need both randomized analysis and amortized analysis to fully analyze these beasts. And so that's the difference, and that's what matters. So, any questions? All right. Enter the tournament. See you Monday.